We're going to talk today about temperature, thermal interactions, how entropy that we talked about last time, how that helps us understand thermal equilibrium. And we're going to do that in the context of a thing called the Einstein solid. Oh, and I guess before I get started, just issue my usual invitation. If you'd like to come up on stage, raise your hand. We'll bring you up. Always enjoy people who want to maybe hang out and keep me honest if I say something confusing or wrong, especially if you know more than I do about things, which is not unusual. I'm kind of a jack of all trades, master of some, but not all the things that we talk about here. So let's move on to slide 2, where I define this Einstein solid. It's amazing how much stuff Einstein did, how many areas of physics he really did put his hand on. We think of him in connection with relativity, but he did all sorts of amazing things, and was really, in many ways, kind of the father of quantum mechanics as well as relativity, even though he railed against it later in life. But an Einstein solid turned out to solve a lot of problems. We won't go into that. It's just a nice model to apply these ideas of entropy to. It's a simple model in which you have atoms connected to neighbors by spring-like forces, which are it's a pretty reasonable approximation to what happens in many cases. But in particular, in such a way that all oscillations in all possible directions have the same frequency independent of oscillation amplitude. That's what's called a harmonic oscillator. A thing that will oscillate at the same frequency no matter how large the amplitude of that oscillation is called a simple harmonic oscillator. And that's what you get when you put a mass on the end of a spring. If you have a large amplitude oscillation, it happens more quickly. It has to cover more distance each time it oscillates back and forth, and it does because it's attached to a spring that exerts more and more force the farther away it gets from equilibrium. It turns out that it all balances out in such a way that the frequency is the same no matter what the amplitude is. And one of the simple results of quantum mechanics is that a harmonic oscillator can exchange energy, I should have said there, can exchange energy only in integer numbers of basic quanta of energy. So a harmonic oscillator in quantum, a little atomic oscillator, can oscillate at a certain amplitude with a certain amount of energy, or a little more amplitude with a little more energy, or a little more amplitude with a little more energy, and they're all at the same frequency. But it can only oscillate with those amounts of energy. It can only absorb these quanta of energy. It can only give off these quanta of energy. And those energies differ. The quanta of energies are given by Planck's constant times the frequency of the oscillation. Planck's constant being like 6.6 times 10 to the minus 34th joules per hertz. So these oscillators typically oscillate at pretty high frequencies, but not so high that their energies are very large, since that Planck's constant is so small. Each atom contributes 3 oscillators in a three-dimensional model space, in a three-dimensional model. Oh, I've got some extra words there. In a three-dimensional model. That is to say, if you have a model like the one shown on this page, each one of those atoms can oscillate back and forth in the x direction, the y direction, the z direction if you want. They can oscillate toward their neighbors onto the sides, to their neighbors front and back, to their neighbors up and down. And each one of those oscillations is effectively a different oscillator. None of this is really important other than the fact that in a three-dimensional model, if you have n atoms, you'll have 3n oscillators. But we can also talk about two-dimensional models, and we can talk about one-dimensional models, in which case we can just have as many oscillators as we want and just restrict these things to oscillate back and forth. None of this is really essential. We just want to have a model to talk about the multiplicity ideas that we talked about last time. So we'll just consider a one-dimensional Einstein oscillator, Einstein solid. Any questions about Einstein solid? Maybe I said a bunch of things I didn't need to there. They may raise questions, but I welcome them. And welcome, Andy, hero. Thanks for coming.
Good morning.
Good morning. So, absent questions. Let's see, anything. Yeah, go
The
ahead.
Einstein solid is this ideal solid that oscillates. All the particles are oscillating in harmony at the same frequency. This is the idea.
They all oscillate in harmony at the same frequency, but that's not to say that things don't look pretty random because they're oscillating out of phase. Some are oscillating in back and forth. Some are oscillating up and down. Some are doing combinations of both of those. Some are doing combinations of all three things, as we'll talk about again here, maybe in a moment.
What's the normal situation for solids? Like just oscillations that are random frequencies, just whatever. That's the norm.
Well, this isn't a bad model in general, but the harmonic oscillator thing is a little out of, but because if the oscillation amplitude were to get too large, then they'd start kind of in some sense bumping into each other. They wouldn't just have the springs. Of course, there are no springs, so all of these things are
Or the bonds between them
approximations.
will break if it's too high energy.
Say again.
The bonds between the molecules they might break if it's
That's right.
oscillating at a very high.
That's right. Yeah, that's right. They might melt, right? The solid might melt at some high enough temperature, et cetera. So it's not great, but this did solve some. Einstein solved kind of a long-standing problem in heat capacity with this that I won't go into. But if you look up Einstein solid, you'll see some of the nice things that he solved using this model. All irrelevant for our purposes here. So let's go on to slide 3. So we want to find the multiplicity of an Einstein solid in an energy macro state, just to kind of remind you what I mean by that. In this case, we're going to talk about an Einstein solid with a certain amount of energy. And then the question is, how many ways can the Einstein solid have that much energy? What is the multiplicity? Because as we talked about last time, that multiplicity of states is what we mean by the entropy, the number of ways that something in a given kind of macroscopic observable state can be in that macroscopic state. So we want to work toward an entropy, an expression for that multiplicity of an n oscillator Einstein solid in a macro state that's specified by its total energy. So I'm going to give its total energy, and that total energy will be some integer q times that quanta of energy that the oscillators can absorb, epsilon. So epsilon is the quanta. The total energy being stored by the solid is E, and Q is just the integer by which I multiply epsilon to get the total amount of energy being stored by the solid. So the number of possible arrangement microstates for that macro state. So we'll just talk on this page about just a couple of simple examples. If I have one oscillator, then there's only one way of storing Q energy quanta, no matter what the value of Q is. If I have 10 units of energy, the only way I can store those energy is to put all 10 into that oscillator. If I have 150 quanta of energy, the only way I can store it is by putting all 150 into that oscillator. So hopefully just that, even though that's a very simple example, hopefully that will kind of give you a sense of what I mean by microstates and macrostates. There's only one way to store energy, no matter how much energy you have, if you only have one place to store it. So what if you have 3 places to store it, 3 oscillators, and you have 2 units of energy that you have to store? Right? So this is, for instance, because I've chosen n equal 3, this could be a 1 atom Einstein solid, a 1 atom 3D oscillator, which would correspond to a 1 atom Einstein solid, whatever that's supposed to mean, right? An atom that is just kind of connected between walls. and I'm going to store 2 units of energy into it. It's pretty easy to just enumerate them. There's 6 ways of doing it. I can put 1 unit in the first oscillator, 1 unit in the second, and none in the third. And then there's a couple of other ways that I can do things like that, just by choosing which oscillator not to put a unit of energy in. And then, of course, there's 3 ways in which I can put both units in one oscillator. And then it's just a matter of picking which oscillator to put those 2 units in. So there's 6 ways of storing 2 units of energy in a 3 oscillator system. Any questions on that?
Can we not imagine 3 atoms oscillating in one direction? That's not an option, is it? Because then it has to be 6 because they oscillate back and forth like plus and minus on the same axis.
Well, so uh, so you're saying, well, ask the question again. Sorry, maybe I just didn't understand.
For n equals 3, you said this is
Hmm.
one atom with 3 dimensions. So up, down, left, right, let's say in, out.
Okay, right.
Can we imagine 3 atoms instead of one atom?
Sure. Yeah, right. You could have 3 atoms uh, connected to each other. Maybe there's walls on each side. A wall goes to spring, goes to the first atom, through a spring to the second atom, through a spring to the third atom, through a spring to another wall. And now you have 3. And now I'm also going to constrain those atoms only to move back and forth in that same line. Does that make sense?
Yeah, sure. So,
The
when we're kind of calculating the ways, isn't this one like added values now? So one of the models, sorry, the mathematician inside me is itching. One of
hmm
the models is one atom 3D oscillator. Another model will be 3 atoms 1D oscillator.
right.
Yeah, but when you say the number of ways is 6 ways, don't you have to add those up as well?
Oh, you mean the fact that it could be a 3D oscillator versus a 1D
Yeah, yeah,
oscillator, add
like
those,
for n
add.
equals
Oh
3,
yeah.
for n
No,
equal
no.
3, q equal 2, we have to add all the possibilities, all the possible values.
Yeah, no, I'm not. Well, I'm not going to do that. Number one, of course, when Einstein was actually solving real world problems with this, um, he did talk about 3D Einstein solids with lots of particles, each one of them oscillating, and that was it. Um, but this is no. I'm going to start with a physical model and just ask for that physical model. How many ways can I store 2 units of energy if there are 3 oscillators? And by the way, you don't even have to really think of these as physical oscillators. They could just be, and often are electrons. Well, no, they really aren't. They usually are molecular vibration vibration patterns. So I guess that really is true. But I guess well, I'm not completely sure. Well, I'm pretty sure I'm not answering your question. But we, I guess I don't want to get too bogged down in worrying about the answer to your question. But at the same time, I think the simplest answer is just I do want to have in mind something. So if you want right now, just think of the 3D oscillator. Just think of one atom. In fact, I think it really is better, as I say there, if you try to picture the various modes of oscillation. So for instance, if the first oscillation is back and forth, left and right, let's say, and the second oscillation is back and forth. Those would be maybe in the horizontal plane if you want to orient them. And then the third oscillator is up and down, so out of the horizontal plane. Then that first oscillation pattern would consist of an atom that's going back and forth and in and out, right, left and right, and back and forth. And depending on how those 2 oscillations are set up, if they're in phase, they would really look just like something coming toward me and to the left and then away from me and to the right. It would look like a linear vibration, just out of the, not purely left, right, or back and forth, but left at the same time it comes forth and back at the same time it goes right. If they were out of phase, it could be a circular. That 1 1 could represent an atom circling in the horizontal plane, going back and forth and in and out, back and forth and left and right, but just in a way that it was fully back when it was in the middle between left and right, and so on, if you can visualize that. So that 1 1 could be a circle, it could be a line, but it would not have any vertical motion, whereas the second one might have left and right and up and down in the same way. It could be circular, it could be kind of linear, it could be elliptical, depending on the phase, and the third one would be similar. Whereas the final three are very clear. It would be a larger amplitude back and forth, a larger amplitude left and right, or a larger amplitude up and down. There would be no motion in other ways. So the first three have a kind of a phase that I would have to specify, and the last three wouldn't. But once again, spending even this much time on it's not really relevant. I just want to count the multiplicity of the ways of storing these energies.
Something much more simple, John, I just wanted to point out that I think is interesting is that you're specifying you have to store all two quanta, because if you were allowed to store just one quanta, you'd have 27 possible ways, 3 times 3, 3 to the power of 3.
Right. And that's a good point, because I do want to point out that what we want ultimately to get to is a graph of multiplicity for a given solid. We want a graph of multiplicity as a function of Q. So as Q increases, you're going to expect probably, and you'll be wrong as we'll see at the end, but you're going to expect probably that multiplicity will increase as I increase Q. That's generally true, but it's not always true, as you know, Ben. I've invited Benjamin on stage. I don't know if he has a question or not, and I don't see him on stage yet. Okay, well, at any rate, we'll monitor that. Let's move on to slide 4. So what if n is equal to 4 and q is equal to 4? Now it's getting a little complicated, and I haven't enumerated them, but I think you'll agree with me that there are 4 ways of putting all 4 units of energy into one of the 4 oscillators. It might be a little trickier to see that there are 12 ways of putting 3 of the units in one oscillator and 1 in another, right? First of all, I have to pick the one to put 3 units in, and then I have to pick the one to put 1 unit in. That's not so hard, is it? I get 4 choices of which one to put 3 units in. I get 3 choices, finally, of which one to put the 1 unit in. So there's 12 ways of storing 3 in one and 1 in another. Once again, I'm going to put 4 units in every time. How many ways are there of putting 2 units in each of 2 oscillators? Well, it shouldn't be too hard for you to enumerate those and see there's 6 ways of doing it that way. Similarly, there are 12 ways of putting 2 units in one and 1 unit in each of 2 others. And there is 1 way of putting 1 unit in each one. I don't know if there's any questions on that. If you just think about that a little bit, I think you'll see. But it's getting pretty complicated, right? And I'm only up to n equal 4. Ultimately, I need to get up to n something like Avogadro's number, 10 to the 23rd. And I think you can see that this program is going to get really difficult by the time I get even to n equal 10. So I got a long ways to go. But if I add all those ways up, there's 35 ways of storing 4 units of energy in 4 of these oscillators. Any questions, comments?
Well, just the Avogadro's number thing there, I think you're picking that just because you want a reasonable macroscopic lump of something, a 1 mole of something. Is that why you're saying that?
Right. Ultimately, we want to be able to use the theory we're
so 12
putting
grams
together
of carbon 12
deal
or whatever.
With real world problems. Yeah.
Or any fraction of it, by all means. Like even if you want to take like 1,000th of it, that's still a huge number.
Right.
Yeah, but we're talking about a teaspoon of stuff, basically, depending on which element it is.
Right. I probably don't even need to go to Avogadro's number. Go to 1 millionth of Avogadro's number, and we're still talking about fantastically large numbers. So anyway, it is, as I say, it's getting very complicated. We need to be able to do it for larger numbers. So I can, but I won't. It's not too hard. It's kind of a fun little problem to show that the multiplicity in general is given by q plus n minus 1 factorial. That means I take that integer and then I multiply it by itself, subtract 1, multiply, subtract another 1, multiply. You know what factorial is. 4 factorial is 4 times 3 times 2 times 1, etc. Divided by q factorial and n minus 1 factorial. That's actually a general form. And we can check that for the 3 cases that we've talked about. If n equals 1 and q is 1452, then I get 1,452 plus 1 minus 1 factorial divided by 1,452 factorial and 0 factorial, for which we need to remind you that you may or may not have learned that, surprisingly enough, 0 factorial is equal to 1. There's a kind of a complicated mathematical reason for that. Shamash, do you have an easy mathematical reason for why 0 factorial is equal to 1?
Yeah, we can cheat. You can use the definition of factorial that says it's the previous one. So n factorial is equal to n minus 1 factorial times n. And you can use that with 1 factorial, and you can conclude that 1 factorial is equal to 1 factorial, times 0 factorial times 1, and then 1 times what equals 1, 1 times 1. So 0
So an
factorial be equal
induction
to 1.
thing or something. Yeah.
Yeah,
Okay.
something like that. Again, this is you can say, oh, I reject this definition, but this is the easiest way I can do in 30 seconds now.
Right. I like that because the only one I really know is that since the factorial is just kind of a special case of the gamma function, you can use the fact that the gamma function tells you that 0 factorial has to be 1.
Yeah, but then you need that's a very complicated way because
I didn't want to get into that.
to get to the gamma function you have to do analytic continuation of the factorial, and that's just don't do that. No, do induction.
No, I like your way a lot better. So at any rate, it's obvious there that I'm just talking about 1452 factorial divided by 1452 factorial, and that's 1, and that's what we found. So that's good. Checking for n equal 3 and q equal 2, we end up with 4 factorial divided by 2 factorial times 2 factorial. That's 4 times 3 times 2 divided by 2 times 2, and that's 6. So you can check that out pretty quickly, and that's what we got before, so that's right. And then finally, the more complicated one that we did here, n equal 4, q equal 4, that's going to be 7 factorial divided by 4 factorial and 3 factorial. And you work that out a little more. The nice thing about that, you can take the 4 factorial out of the 7 factorial and be left with 7 times 6 times 5, and then just have to divide it by the 3 factorial, which is 3 times 2. Yeah, times 1. I forgot the 1, but you'll excuse me there. I think that works out. And I get 35. So that's what I got up above by enumerating them. So it gives me some confidence that I may have a formula that works. It doesn't prove that the formula works, but I can prove that without too much difficulty, but I'm not gonna. So that's the formula. Now let's do a more complicated case. Let's look at a case where I have 10 oscillators, and now I'm going to do what I was saying I wanted to do. I want to plot the multiplicity as Q grows. So you'll see over there on slide 5, you'll see a table for you. 10 oscillators. When Q is equal to 0, when there is no energy to store, there's exactly one way of doing that. When I have 1 unit of energy to store, there's 10 ways of doing that. I just have to pick which oscillator to put it in. etc. And you can see already by the time you get to 2, it's getting a little more complicated. By the time you get up to 10, 92,378 ways of storing 10 units of energy in 10 oscillators. When you get up to 20, what is that? 10,015,005 ways of storing 20 units of energy in 10 oscillators, etc. And you can see, as we suspected, that the multiplicity, which I'm calling omega here, sorry, there's too many words for all these things. Multiplicity, omega, those are the same thing, is growing very quickly. So what I've done is I've plotted the multiplicity as a function of Q. First, the first graph up there at the upper left, sorry, tops out at 200,000. And we get to 200,000 by the time we get to what, 12 oscillator, 12 oscillators, 11 oscillators, 12 oscillators. So that graph goes right off the scale by the time I get to 10 or 11, 12 oscillators, as you can see. Peaks at 200,000 there. So then I increase the scale to 2 million, going up to a multiplicity of 2 million. We get to 2 million when we get to about 16 oscillators, etc. So each one of these, I'm just changing the scale on the multiplicity thing. And what you notice is that no matter what scale I choose, it looks like the multiplicity is basically 0 until you get to some place where it then just takes off. And that should be, for those of you who have any kind of recollection of what you did in school or maybe are practicing scientists, that should be reminiscent of what we call an exponential function. Looks a lot like an exponential function in the sense that no matter what scale I plot on the vertical scale, I get something that looks like it's 0 kind of for a very long time, and then all of a sudden starts growing and then just grows so quickly that it shoots off the top. So I guess I'm answering my first question. Does that look exponential? Yeah, it kind of does. But does it really look exponential? And can anybody tell me why it doesn't look exactly exponential?
It's very asymptotic to 0 for a long time. An exponential starts at a certain value, like it starts at power 0 equals 1 or something, and it touches 0 at minus infinity usually.
Yeah, okay, that's true. I'm certainly not going to worry about the negative extension here. There's something about the shape of these graphs that should tell you that this is not exponential. And it's important for the thing that I'm talking about, that I'm not changing my horizontal scale at all. I'm only changing the vertical scale. It's a little subtle. I'm just curious if anybody, this is your chance to shine. Oh, let's see. Let's get Ben up here again. He may even know the answer. He swiped the wrong way, obviously.
Yeah, I'm afraid I did. I was also wondering if just saying that, you asked about 0 factorial being 1. I'm wondering saying if you consider factorial the number of ways to arrange things where order matters, then the number of ways of arranging nothing is 1. A bit like the first entry in your table. It's a bit of a hand wavy thing. But
Yeah, I don't think, right. I'm not sure because the number of ways is really a combination thing, which has to do with ratios of factorials, et cetera. The real question here is just nakedly, what is 0 factorial?
yeah, mathematically.
Anyway, but does anybody want to, I'm tempted to just wait a moment longer because this actually turns out to be very important. Not only is it subtle, but it's also really important for everything we're going to be talking about from here on out. And the question is, so second loss, what's the question? The question is, what is it about these 3 graphs, which are it's just the data that I've got over there plotted with different vertical scales. What is it about these graphs that tells you that it's actually not an exponential function?
It looks to me like the inflection is similar. but the point at which the inflection begins is changing in the graphs.
That's right. The point at which you kind of see it start to take off is moving out. But that's also characteristic of an exponential. Problem is you just can't plot an exponential function, really on one graph and see it all because it grows so quickly that you're just bound to have the early part look like it's just zero. And so it always has to, at some point, take off. And the point at which it takes off is going to move out to the right when you go to larger and larger vertical
But
scales.
they also, in that case, they none of them really become asymptotic at the to the vertical rise. They all have a less than 90-degree angle at the end.
That's right.
And I think an exponential, even if you scaled it as you just said, problematically or not, could terminate in a visibly indistinguishable angle to 90.
Yeah, but that too turns out not to be true. That you might think that, but an exponential is not an asymptotic function. It has no asymptote. So that's also
But that's not an asymptotic proposition.
these the
To say that it
exponential. There's no
rises,
value.
just
I was just going to say there's no value of x for which there isn't a perfectly finite value of y, and so it doesn't terminate.
We
An
call it
exponential
asymptotic.
function
We call it
will
asymptotic
always
direction.
look the
It's
same.
not an
Sorry?
asymptote.
but when I use the term asymptotic here, it's a little bit inaccurate. And that's because I don't have a term to describe
There
what
is
the
a
slope
term.
would look like if it well, it would approach a final x, right? That would be asymptotic to a
No,
final
it
Yeah,
x
doesn't.
if it was
but
vertical.
this one doesn't. Yeah, this one doesn't. So
Doesn't.
we call it an asymptotic
It has
direction.
to be it has to be visibly
So
asymptotic.
I think, isn't
At
it to do with
scale.
the rate at which the growth grows, John? Something like the second derivative.
Now you're talking. Say a little more.
So with an exponential, the growth rate would always increase and never slow down, right?
Okay, yeah. So
So the
So
growth
tell
of an
me what it is
exponential would
that you're
just.
seeing. What is it that you're seeing that's making you think this isn't exponential?
He's
Well, I'm
saying the
trying to.
same thing I'm saying. He's just describing it in different words.
Well,
Can I try again?
I'm trying to say that if you
let's.
kind of hold a pen along the graph and look at the rate at which the slope increases, I don't think the rate at which the slope of this thing increases keeps increasing.
It does. The rate at which
Does
it
it?
increases does
Yeah, no,
keep
maybe it does. It's
increasing.
quite qualitative. Yeah, no, I think it probably does. It's
So
really difficult to
Benjamin,
pin down. Yeah, it's
you
difficult
try
to pin
again,
down.
then we'll let logic maybe.
Well, I think Ben is on the right track. The increase, never mind the rate, but the increase, the inflection point is identifiable. And
Well, I don't know. I don't
in
think
an
that's true,
exponential
right?
curve,
That's your subjective.
I
It's
think
a
it is the case that there's if I was driving on this curve, there's definitely a place where I would feel the most gravitational inflection.
Fair enough. If you treated it if you drove along it at constant velocity, I agree with you on there. Yep. But strangely
point,
that depends on the scale
point.
that I choose for the vertical
It
axis.
does. It does. But I think that on any exponential graph, the right-hand side needs to continue to become steeper. And that means it becomes asymptotic to a 90-degree angle on any exponential curve.
Well, that's whatever it is you're saying is characteristic of an exponential, and so I don't.
Oh, these have fairly straight lines on the right-hand side. After the inflection point, they're fairly straight, much straighter than the inflection point itself, and they're not
Yeah, that's
vertical.
just
They
but
should be straight, but they should not be straight at an angle. They come to a straight line.
Well, an exponential would do exactly that. An exponential curve would do exactly that.
We'll have to plot an exponential curve and have a look-see. I think I'm right.
So let me. I don't know unless Shamash, did you have something you wanted to say?
I'm not sure anymore, but I'm just gonna throw this. So for an exponential, what I'm expecting is as I make the y unit smaller, so as I decrease, let's say stretch downwards that y axis, as I compress it, what I'm expecting is to see more vertical, and then the distance on x to be shorter to the inflection. Whereas here, what we see is as you squeeze that y direction, it's becoming longer.
Well, but once again, that is to be expected, and you will see that with an exponential curve as well. If I make a larger scale, then it'll just take a lot longer for it to look like it's not zero anymore.
But we're keeping the x fixed here. This is the trick. So the
Right.
x is staying fixed. If you compress the y direction, you should be seeing that asymptotic direction towards plus infinity become quicker. Not take more time. Whereas here, as you have on the bottom right, 2 times 10 to the power 8, it becomes a little bit slower, and this is not what we expect.
Oh, okay. So I wasn't. Yeah, what you just said is, I think, maybe really to the point, but I didn't think that was where you were going when you say it's a little slower. Let me suggest this, because I think the simplest way to see it is that if this were an exponential curve, then I could take all 4 of those and just shift them left, right, and put them right on top of each other. I could shift those things to the left and right, and the curves would sit right on top of each other. They would look exactly the same. I would just have to get rid of some of the part that looks like it's down there at 0. If I took that second one and shifted it 5 units to the left, it would sit right on top of the first one. And if I took the third one at the lower left and shifted it about 10 or 15 or 12 units to the right, it would sit right on top. And you can see for sure that that's not the case. Maybe it's what all of you were saying at some level. I don't know. But it just looks less steep, right? As you change the vertical, it looks less and less steep. An exponential wouldn't do that.
Is that true even if you're scaling the vertical axis without scaling the horizontal axis?
It's true only if you scale the vertical without scaling the horizontal.
Oh, if you simply zoom in and out on the graph, then that's not true, what you're saying?
Yeah, that's
sort
right.
of fractal nature of it?
Let's see. Is that right? I don't know. Is that right? Maybe that's right too. Let's see. I have to think about that one a little bit more.
The way I would want to try and put it as simply as possible is that the rate of increase of slope is not smooth in these.
Right. That's right.
Which is kind of what I said about the second derivative, but I just didn't.
It is right that
I just
the
didn't
second
say
derivative
I didn't
does
say it in
continue
English
to
as clearly as that.
increase.
Yeah.
Right. But it doesn't increase at the right rate. Yeah. Anyway, sorry, we spent a lot of time on that, but this is really an important point that that graph, if you were to try to fit an exponential to that first curve, you would give it a certain rate constant. We would say in mathematical language, it would have a certain rate constant. The rate constant for the second curve is smaller. It's not the same rate constant. Apparently, if you try to fit an exponential curve to that second one, it would be a slightly smaller rate constant. And for the third one, slightly smaller yet, and for the fourth one, smaller yet. And that's reflected in the fact that the first one really takes off. The second one, doesn't take off quite as quickly. The third one, not quite as quickly. And the fourth one, not quite as quickly. I'm not talking about where it takes off. I'm talking about after it takes off, how quickly does it take off? Forget about all of the 0 part. Just look at where you start to see it go up.
So 30 seconds here. If I have e to the lambda t or e to the lambda x, which is what we're expecting here, you're proposing that the lambdas are becoming smaller as...
Exactly.
Okay, cool.
Exactly. Right. And
so
let's move.
These two functions aren't, they cannot be transformations of one another, because the actual constant is changing before x, not the constant before the function, which is a vertical transformation. Yeah, okay.
Exactly right. Yeah.
Somehow this makes more sense to me than the other English. That's how I messed up completely.
Okay, that's good. So, I mean, maybe, and it may be, I apologize if I just didn't, if you were trying to say the same thing that I did. It is a little complicated, but I think the simplest way to see it really is, as I say, by the fact that if you were to just plot all those, take all those graphs and just shift them left and right, you would see that the lines don't sit on top of each other, and they would if this were an exponential function. So, and that's best reflected on the next page by the fact that if I take the natural logarithm, if I take the logarithm of an exponential function, what I get is a linear function. When I take the logarithm of an exponential function, I get a linear function. In this case, I don't. The natural logarithm of this function is a function, is not a linear function. It's a function that importantly curves downward. It's really important that it curves downward. The logarithm of the multiplicity function is a downward curving function. And that is just generally true about multiplicity functions. So I'll just take, I don't know if there's questions on that, but I just want to take a moment on that to once again just emphasize that that's really central to everything that we're going to do in the last half of this.
I'm not sure why are we expecting an exponential. We started with factorials. Like, this is where I'm at.
Oh, yeah, no, and I didn't want to imply that we were expecting an exponential, but I did want to point out that it does kind of look vaguely exponential,
I see.
and it isn't. Yeah. Okay, so that's good. So this is now the logarithm of the multiplicity function, and I'm telling you kind of early on, this is entropy. Entropy is the natural log of the multiplicity function. So we, in some sense, we're really done. And this is for many of you, this may be the most accurate definition of entropy you've ever seen, because people say, well, it's a measure of disorder, etc. No, this is what entropy is. It's the natural log of the multiplicity function. And you kind of understand what multiplicity functions are.
Can you give me that John voice with the echo on your mic when you say that again?
This is the, yeah. I don't have reverb. I guess I could put it on in Clubhouse. But okay, so good. Shall we move on? Or any other comments on that? So let's move on to 7 now. So we have been talking about a single Einstein solid and the way, and now we know the way the entropy, go back to 6 for a second. So this is the way the entropy, if you want, just the natural log of the multiplicity function. It's the way that thing depends on how much energy is put into that solid, because Q is just an integer that represents how much energy I'm storing in the solid. As I increase the energy, the entropy increases. And it's really important that the way the entropy, you notice the entropy does increase, but it increases rapidly at first, and then less and less rapidly as the energy increases. Down there, when there's almost when Q is 1 or 2, the entropy increases a lot with each additional quantum of energy. And later on, it increases less with each additional quanta of energy. Okay, so in 7 now, we're going to talk about 2 of these Einstein solids right next to each other so that they can exchange energy. In some ways, you might say, well, isn't this just a bigger Einstein solid? Well, yeah, it really is, right? But I kind of want to think of maybe putting the 2, keep a little space between them so they can kind of bump into each other and exchange energy. They have kind of a weak connection, so they can exchange energy. But fundamentally, they really are they have their own character. So I can really still talk about now 2 Einstein solids that are exchanging energy. So I have each one of them. I know how each one of them, I know how the multiplicity of each one depends on energy, and I can calculate that. So in particular, I'm going to talk about a really simple case. One Einstein solid consists of 3 oscillators, just 3 oscillators, 1 atom if you want in a 3D, but let's not make it that because I'm going to have another one with 2. So one has 3 oscillators, one has 2 oscillators. And I want to store a total of 5 units of energy in these 2 Einstein solids. Now, just to give a physical picture, I might have started with all 5 in solid A. I'm going to argue I think I can argue already that that means that solid A starts out really hot. It's got a lot of energy in it. If it has all 5 units at the beginning, then solid B has no energy in it and it's really cold. That should make kind of sense. We're going to get those definitions a lot more solid here, so to speak, in a moment. But that's what I've got. And I can now, but now I am going to store 5 units in the 2. And so now the question is, if I store, how do the multiplicities depend on how I divide the energies between the 2? So in the table there at the left, the first row says, let QA be 0. So let's put no energy in solid A. We already know how to calculate the multiplicity. The multiplicity of A is 1. There's only one way to store no energy in solid A. But if solid A has 0 units of energy, then solid B has to have 5 units of energy because there is a total of 5 units. And I know how to calculate its multiplicity. 5 units of energy stored in a 2 oscillator Einstein solid. There's 6 ways of doing that. So that's the multiplicity of B. Now the question is, how many ways are there of storing 0 units in A and 5 units in B? And the answer is, well, there are 6 ways of doing that because there's only one way of doing that in A and there's 6 ways in B. So that means there's 6 ways total. Now this will get a little better if I go to the next row. Let's go to the next row. If I store 1 unit in A, then I have to store 4 units in B. And if I store 1 unit in A, the multiplicity of A is 3. And if I store 4 units in B, its multiplicity is 5. So how many ways are there of storing 1 unit in A and 4 units in B? Well, the answer is 15, right? There's 3 ways of doing the A thing, 5 ways of doing the B thing. And so I can do them in any combination. And that means that there are 15 ways. I've got 3 choices for how to do the A thing, and I got 5 choices for how to do the B thing. So that's 15 ways of doing that. Okay? Question? Is that clear? And so on. So I continue the table. 2 units in A, 3 units in A, 4 units in A, 5 units in A. And there's only six rows in this table because there are 5 units of energy. There's only 6 ways I can partition the energy. And the last column in this table tells me how many ways what is the multiplicity of each of those partitions. There's 6 ways of partitioning 0 and 5, 15 ways of partitioning 1 and 4, 24 ways of partitioning 2 and 3, 30 ways each of partitioning 3 and 2 or 4 and 1, and 21 ways again of partitioning 5 and 0. So just looking at this table, hearkening back to what we did last week with the dice, the whole idea of multiplicity, the high multiplicity states are the ones we expect to see, because if I just kind of roll the die, if I roll the dice, I'm going to find the ones that have the most ways of letting them happen. And so I expect the partition probably to be 3 and 2 or 4 and 1 here. And that's reflected if I just plot the multiplicity, as I do on the right, as a function, notice, of QA. So I'm plotting the multiplicity as a function of the energy in A. And it's important for what comes on to realize that, of course, as I go to the right on my horizontal axis there, I'm decreasing the energy in B. As I increase the energy in A, I am decreasing the energy in B necessarily, because the total is 5. So that's what the multiplicity function looks like. I'm not doing the entropy. This is the multiplicity. I'm not taking the natural log. I'm just plotting the multiplicity. Okay. And the next slide just extends this. Now, all I'm doing in the next slide here is I'm scaling up. So at the top there's the what we just did on the previous slide. At the lower left, I'm showing the same kind of calculations, except now I have 4 times as many oscillators in A, 4 times as many oscillators in B, and 4 times as many energy units to store. So I'm just kind of scaling it up, right? 4 times everything, 4 times as many oscillators in both, 4 times as much energy to store. And what I want you to notice is that whereas that first curve, it just looks like kind of a dull, shallow peak, the peak is now starting to sharpen around 12 in this case, which happens to be 60% of the total energy. 60% of the total energy is being stored in A. And that means that 40% is being stored in B. And it's sharpening. And then in the final one, I go to NA equals 60. I take the initial, what I did on the previous slide, and I multiply everything by 20. 20 times as many oscillators in A, 20 times as many oscillators in B, 20 times as many units of energy to store. And it sharpens more. It's still sharpening around the 60% thing. 60% of the energy is being stored in A. But now that's a much sharper thing. Whereas even in the second example, you'd expect to see occasionally, what is that? I guess that's 20% of the energy in A. That's the 4 units of energy would be 20%. You'd expect to see that sometimes. You can see it's not 0. It's getting down pretty low, but you'd expect to see that sometimes. How often would you expect to see 20% in the final example? 20% now is way down there at the 0. This curve has come down to what looks like 0, really, really 0, long before you get to 20%. So if I have 60 oscillators in A, 40 oscillators in B, and 100 units of energy, I'm never gonna see just 20 units of energy in A. That's a really low probability thing. And notice the scale here. That's 10 to the 57th on the upper scale. If you try doing factorials, when you start, you're doing factorials like 100 factorial when you calculate these multiplicities. Most calculators will choke on trying to do 100 factorial. So these numbers are enormous, and we're just talking about a handful. This is a tiny, tiny Einstein solid, and look how sharp that thing has gotten. Imagine how sharp it might get if n goes from 60 up to 10 to the 20th. And the answer is it gets really, really sharp. So let me stop there for a second, and then we will go to 10 to the 20th and talk about that for just a moment.
I'm amazed. Can I just drop that?
It is amazing, the numbers here, and I decided I wasn't going to talk about this, but the kinds of numbers you get are numbers like, when you start doing these multiplicities, you get numbers like 10 to the 10 to the 23rd. That's an I mean, it's hard even to imagine what that is. That's 10 raised to the power a number with 10 to the 23rd. What do I say? Yeah, 10 to the
So
23rd, right?
it's not 23 zeros after the 1, it's 10 to
It's
the 23 zeros after the
There
1.
you go. That's what I wanted to say. Exactly. 10 to the 23rd zeros after the 1.
Yeah, that number has 10 to the 23rd digits.
Yeah, right.
That's a big ass number.
It's such a big number that if you multiply 10 to the 23rd by 10 to the 100th, a googol, right? You know what a googol is. A googol is 10 to the 100th. If you multiply 10 to the 23rd by a googol, what you get is 10 to the 10 to the 23rd.
Yeah, it's the sort of
Because
number where if you do it in normal kind of book print size on a piece of ticker tape and then let that tape all kind of curl up like a ribbon, it's not clear it would fit in the galaxy or even bigger.
oh
Right.
no, it won't fit in the universe at this rate. There's no way. It's bigger than the radius. What is the radius of the universe? 45 light years? Billion
Well,
light years? What is it?
I'm saying if you put it on a piece of paper and then kind of fold it up, it's not entirely clear how. Depends what volume you assign to each digit, but you could assign a cubic millimeter to each digit and then work out just how big that is. But it's pretty huge.
Right. So let me just take
But
it to
I'll do that and put that in the chat. I'll assume there's a cubic
okay.
millimeter assigned to each digit, and then we'll tell you what the volume of that is
Yeah,
and what that looks like.
make sure we have enough particles for this. Like you have 10 to the 80 particles. Even if you collect all the atoms in the universe, you're still gonna need to fold at this rate.
So there was one thing I guess I didn't say on slide 8 there. I'm just saying this. I'm not showing this to you, but it can be shown that the so-called width of this peak, if you come down halfway, the width of that peak is something like 1 over the number of particles to the 1/2. So in very rough figures here, in the last case at the lower right there, where I have like 100 particles, 1 over the square root of 100 is 1/10, and so the width of the peak. Let's see. Did I say that right? I shouldn't have said it. I didn't mean to say. What I meant to say was Q over n to the 1/2. It's the total number of units of energy divided by n to the 1/2. So if I take the 100 units of energy and divide by 100 to the 1/2, that's 10. I get 10. The width of that peak should be something like 10. And you can see that's, it's not exactly right here. It looks like the width of that peak is maybe more like 20. It extends from maybe 50 to 70. So it's not exactly right. But factors of 2, when you're talking about things like this, you just don't really worry about. And when you get down, and when we go then to slide 9, if I talk about when n equals 10 to the 18th, yeah, once again, I've kind of screwed things up here. But 10 to the 18th, square root of 10 to the 18th is a billion. So 1 over a billion is a billionth, and it should have been 1 billionth of the total energy there. The peak comes in very sharp on 60% of the total energy. As long as I scale everything like I was doing, I was scaling everything up by the same factor. So one system is 50% larger than the other, always has 50% more particles than the other. The thing will sharpen up on 3/5 of the energy being, 60% of the energy being in that larger system. But the width now is 1 billionth of the total energy. And what that corresponds to is that in this case, if I were to draw this graph with a horizontal axis that were 1,000 miles long, this peak would have a width of a 20th of an inch. So that's how sharp this peak is. I'd have to draw this graph with a horizontal axis 1,000 miles long this peak would have a width of a 20th of an inch, and then it would come down to, for all intents and purposes, zero beyond, certainly beyond an inch on either side. It would be zero. The probability of ever getting any energy distribution other than the one at the peak is so small that you can show things like you would have to wait a Google times the age of the universe to ever have a chance of it ever appearing to be distributed like that. And this is why these what are ultimately probabilistic laws have the force of certainty. You can bet your life on these low probability events never happening, because that's how low the probability is.
John, that 10 to the 10 to the 23. So it's actually surprisingly, if you to write that number out, to be clear, every digit of it, all 10 to the 23 digits, if you assign a cubic millimeter to each digit, which is reasonable small print on a thin tape, you bundle that tape up like a ribbon completely tightly with no space in between, it's 30 by 30 by 30 miles. So it's a city extending up to 150,000 feet. So, I mean, it's on one hand, that's astronomical, but it's also, it's a lot less than I thought, actually.
Well, it's pretty good. It'll work for me. Yeah, that's anyway. But it really is the math of large numbers is really pretty remarkable. You start with, I said before, you start with things like this. If you add 1572 to 10 to the 23rd, what you get is 10 to the 23rd, right? Because the fact that you said 10 to the 23rd suggests that you really don't know anything about those digits down there near 10 to the 1 and 10 to the 2 and 10 to the 3.
Doing that addition is so expensive now. Like if you want to code for a computer program to actually do that addition with very large numbers, you're gonna have to invent, like you're gonna have to write a new class,
Takes a lot
because
of
most
memory.
because you have to define it as an array now. You have to store all the digits and then define addition all over again. And even then, you will print a huge sheet of 1 0 0 0 0 0 0, and it goes on forever. And then you'll find like 2 3 at the end, which is like, who cares?
And of course the problem is it's fine. So when we say that 10 to the 23rd plus 1500 is 10 to the 23rd, that's fine until further down the line you want to subtract 10 to the 23rd from the result. So then you have to be careful.
Now you come back to me. You're like, oh, where's the mathematicians? We can't do pi equal 3 anymore. No.
Okay, well, let's move on to slide 10, where we're going to really get back to that. So what is the condition for the highest multiplicity macrostate? What is the condition for that? And this is where we really see the utility of the entropy function. When the total multiplicity, remember the total multiplicity is the product of the two. Now we're talking about these interacting solids. What determines that macrostate, that division of energy that's the highest probability? When omega total is largest, then of course the natural log of omega total is largest, because natural log is a function that always takes a bigger number into a bigger number, a number that's, if I have two numbers and I take the natural log of them, the one that's bigger will have the bigger natural log as well. So I can talk about omega itself being largest, or I can talk about the natural log being biggest. But the nice thing about talking about the natural log being the biggest is, since the omega total is just the product of the two multiplicities of the interacting objects, the natural log of omega total is natural log of the product of the two multiplicities, and that by a property of the natural log that you may or may not remember, the natural log of a product is the sum of the natural logs. So I can add the two natural logs to get the natural log of the total multiplicity. And this is now finally where it comes into play. So let's let's first of all, on the right, let's look at the graph. I'm graphing the total entropy now, the natural log of the multiplicity, as a function of the energy in system A. That's important. I'm talking about the energy in system A. Remember, the total energy is constant, but I can choose to apportion the energy in any way I want between the two. I want to know which one's the most likely. So the blue graph there is the entropy of system A as, and I'm plotting it as a function of its own energy. So you see it doing that. It's increasing, but remember, it increases rapidly at first and then less rapidly. In other words, it curves downward. So that blue line is the entropy of system A. The red line is the entropy of system B. And you may say, well, wait a minute, why does it look like that? It looks like that because for B, the energy is increasing toward the left. Remember, B is whatever's left over after I remove Q from A. So QB will be 0 when all of the energy is in A, and it will be all of the energy when there's 0 energy in A. So basically, the plot of entropy for system B is just kind of a mirror image of what it would look like if I just plotted it the way I would normally plot it. So I plot the entropy of B as a function of the energy in system A, and I get that red curve. Now I add those two natural logs to get the natural log of the total. That's the big, heavy black line at the top. Clearly, when I add those two, I have to get the entropy of B when there's no energy in the system. In other words, that black line has to intersect the red line at the left end at QA equals 0. And it has to intersect the blue line when all of the energy is in A, because at that point, remember, I'm adding these two. So whenever one of them is 0, the total has to just be equal to the other one. And that happens at both ends. So that black line is equal to the red line at the left, and it's equal to the blue line at the right, because the other two are 0. But in between, what happens? Well, at the beginning, since A is increasing fast, the total goes up. But now B starts decreasing more and more quickly. B is decreasing more and more quickly. A is increasing less and less quickly. The peak value, and this is a little tricky, but you need to kind of just think about that. The peak value occurs when the rate at which A is increasing is equal to the rate at which B is decreasing. At that point, the sum isn't changing. When I get to the place where A is increasing at the same rate that B is decreasing, then the total isn't changing. And beyond that point, since B continues to decrease faster and faster, and A continues to increase slower and slower, it starts coming back down. Okay, so I say that, I will answer questions on that if they are. But the key takeaway here is that the peak value occurs where the slope of that A curve, the rate at which it's increasing, is equal to the slope of that B curve, the rate at which it's decreasing. And that's represented by those dotted tangent lines. Those dotted tangent lines have to have the same slope, or if you want, equal and opposite slopes. But remember that B is only a negative slope because I've kind of plotted it backwards. Its energy is increasing toward the left. Sorry, that's a complicated slide there. Any questions I can put out, or did anybody have a better way of saying what I tried to say?
I don't know if it's a better way, but we can derive ln omega, and then it'll be the derivative of ln omega a, and then the derivative of ln omega b, which is 1 over, whatever the function u
That's
prime over
right.
u plus. But I'm not sure if that's a better way.
Well, it's not a better. It's a way I'm strictly trying to avoid, although I'm going to pay lip service to it on the very next slide. Um, we're talking. It's probably worth saying that everything I'm saying here is I'm talking about calculus. So if you followed it and you've never taken calculus, congratulations. You know, you understand now a little calculus. But that's exactly what we are talking about. Calculating slopes of curves and slopes of curves, et cetera. The rate at which the curve slope is changing is what we call a second derivative, et cetera. So all of these things are calculus ideas, but I wanted to say them in just normal terms, because you really can't understand this just by understanding that the total entropy is just the sum of the two entropies. And the place where it peaks will be the place where one entropy stops increasing faster than the other one is decreasing. And that's exactly what we find when we find the place where the slopes are the same. Go ahead, Ben.
Yeah, I was just slightly concerned. It's fantastically rigorous approach, and it's cool. I just wonder if the meaning may be slightly lost in the details. I, um, oh, my doorbell's just gone. I'll go get the doorbell, and then I wonder if it might just be worth recapping it for a system that just has maybe a few particles, 4 or 5, in 2 possible states, ground or excited, and then thinking about the possible. Think you can very clearly see how the disorder, the entropy increases and decreases then. So it might
Right.
be worth just talking through that for 2 seconds. But I've got to answer the door, and then I'll be back.
Okay.
I'll address a point in chat then, as we wait for Ben. Gokul 5 minutes ago or something, he wrote P of A union B is equal to P of A times P of B, as long as the events are independent. I'm not sure if this is relevant here. I think you wrote it when we were talking about omega t being equal to omega A times omega B. So maybe John, you can speak about that if this is what we're doing here or something else.
Yeah, right. I'm not really talking about probabilities here. I'm really just talking about mathematics. The probabilities are kind of implicit in the multiplicities, but ultimately I'm just talking about a situation where the total multiplicity of a system of two objects, Einstein solids, if you want, but it doesn't have to be. This is true in general. Multiplicity, two interacting, two thermally interacting is really also what we're talking about. Systems, two thermally interacting systems, each has their own multiplicity. The total multiplicity associated with any specified partition of the energy, that would be the macro state specification in this case, is the product of the two multiplicities. They are not themselves probabilities; they're just multiplicities, and
Maybe
then it's just uh, and then it's just the case that the natural log of that total multiplicity is therefore the sum of the natural logs of the two multiplicities, because of the fact that the total multiplicity is the product of the two multiplicities.
maybe said very simply, if you imagine that the multiplicity of B is 1, so there's only one state in that solid B, and then the system B, let's say, and then in system A, there's a bunch of stuff happening. So what's the total multiplicity? Well, it's just the multiplicity of A, because B
Mm-hmm.
is just one state. Whereas if you have 2 states, let's say, that B can be in, then you have to calculate all the variations of A for the first one in B, and then all the variations of A for the second one in B as well. So that's where the multiplication comes from.
Right, and we talked about that a little bit in a very small number Einstein solids on slide 7, just to remind you, when we actually explicitly calculated the multiplicities for system A having 3 places to put energy and B having 2 places to put energy, and then having a total of 5 units of energy to put in. And then we've been kind of scaling that up, keeping the same proportions for the numbers and the amount of energy, et cetera. So if you look at Oh, let's see, what did I say? Did I say that right? Multiplicity. Yeah. So sorry. So that's right. So in the case of the interacting systems, that multiplicity has a peak because it's the product of one thing that is increasing as QA increases and another thing that's decreasing as QA decreases, increases, sorry. Is Ben back?
Yeah, I'm back. So if you stop me if I make a mistake, 'cause I'm just trying to do it off the top of my head without a piece of paper in front of me. But let's imagine a system where n equals 5 and q equals well, actually q is, we're going to add quantas of energy, 1, then 2, then 3, then 4, then 5, something like a lasing medium that can take that. And you have 5 particles, and initially they're all in the ground state, so they can only have 2 states, ground state and excited state. I
Well,
like
now
to,
so if you are going to talk about the lasing kind of system, maybe hold off for just a little bit, because so far we're just talking about places where we can put in any amount of energy, and I do want to then say, well, what happens when these places can only store a maximum amount of
Oh,
energy?
okay.
There's a
Okay, cool. I'll
limited
come back with it
number.
then. But like as a
Yeah.
recap at the end, it might just be worth talking through. I just imagine marbles, and I'll maybe talk through it for 2 minutes and just
Yeah.
tell you how I
Well,
see very simply how we flip into negative temperature.
yeah, I'll pretty
So
much
let me
hand
know
it
when
over
that's a
to
good
you when
time.
we get there. Yeah, that's
Okay,
good.
cool.
We'll get there very quickly because we're almost done. So this condition that the slopes be the same, on slide 11, I just point out, as Shamash was intimating, this is in the language of calculus. What we mean here is that the derivative of the entropy with respect with respect to energy, the derivative of the entropy with respect to energy, that's the slope of the entropy versus energy curve for A, has to equal that same derivative for B, the derivative of the entropy of B with respect to its energy, at the place where the total multiplicity maximizes, which will be the most likely macro state, the most likely partition of energy. And it's really, if you think about it, I mentioned, suppose we had started with all of the energy in one of those systems. Well, that's one of the possible micro states. That's one of the, but it's not, but there are many more microstates associated with the macro state that has that maximum entropy. And so this is where we expect it to come to as the two objects equilibrate. Well, what are we talking? We're talking about thermal equilibrium. This energy jostles around and eventually it partitions itself in a certain way. What is that way? The way where these derivatives are equal. That's the time, that is the condition that we recognize as thermal equilibrium, by which we explicitly mean that the two systems have come to the same temperature. And so we recognize that calculus thing that I just said, the slopes are equal, is equivalent to saying that the temperatures are equal. It is, in fact, the microscopic basis for the idea of temperature and thermal equilibrium. And the only problem with what I've written at the top is that because of the downward curvature of the entropy versus energy graph, the slope DSDE, that thing that I wrote at the top of this page, is getting smaller as we add more energy. As we add more energy to a system, the slope of that curve gets smaller, not larger. So we can't identify the slope as the temperature. It just becomes more convenient to say, well, if we're going to define a temperature, we should define it as 1 over the slope, ds dE to the minus 1, or just dE ds, the rate at which the energy increases as the entropy with entropy. So we just define it to be the other way around. And then I'm just kind of giving you a simple result here. Notice I haven't talked about this yet, but energy is measured in typical units as joules. Entropy, what are the units of entropy according to everything I've said here so far? Well, entropy is the natural log of a number. So what are the units of entropy as I've been defining it?
Units less.
It units less, right? It has
I was
no
about to say
units.
gradient or something.
Yeah, no, it's not a radian either. You could put radian in and it would be fine, but then you'd confuse people. Yeah, it's unitless. And so this unit of the temperature that I've defined here has units of energy. It's energy divided by a number. And I'll just tell you here that in a typical chunk of matter, if I have a little teaspoon of matter or well, just a typical chunk of matter. If I'm just holding a chunk of matter in my hand, typical chunks of matter have the property that their energy increases at the rate of 4 times 10 to the minus 21st joules when the entropy increases by 1. When the entropy increases by 1, the energy increases by 4 times 10 to the minus 21st joules. This, I'm just telling you a fact of nature here. This is a kind of an interesting fact of nature. And that amount of energy is what scientists often, we use units of electron volts. An electron volt is a very tiny unit of energy. It's the amount of energy an electron gains when it is accelerated through a potential difference of 1 volt. And it's very typical. If you tell a physicist that the temperature is 1/40th of an EV, they'll say, "Oh, good, it's comfortable. I'm pretty comfortable at 1/40th of an EV. I don't need a sweater. I don't need to jump in a pool. I'm not too hot. I'm not too cold. 1/40th of an EV that's room temperature," and that's exactly right. So we could really just close. I could end the entire thing right here and just understand that we measure temperature in electron volts if you want, or joules if you want. But that's not what we measure units of temperature in. We measure them typically in degrees Fahrenheit or Celsius. In the situation we're talking about here, it probably won't surprise you to know that Fahrenheit or Celsius won't really work because they have this weird property of having an arbitrary place where there's 0. We have to use what's called an absolute temperature scale. Oh, I just realized I forgot to edit these 2 slides. I have a little repeat at the top of slide 12. So there's a little repeat. And we recognize that as roughly room temperature, perfectly appropriate unit of temperature. The precise conversion from joules to Kelvin, and this really is the precise conversion for units of temperature in joules to units of temperature in Kelvin, is that 1 Kelvin is equal to 1.380649 times 10 to the minus 23rd joules. So a temperature of 1 joule is really hot, like 10 to the 23rd Kelvin. That's really hot. But that's the conversion from units of temperature in Kelvin to units of temperature in joules, or vice versa. So we could just leave it there and just convert every time we needed to, but it's much more. It's completely conventional. In fact, it really stems from classical thermodynamics, which happened before we really knew what entropy was, to change the definition of entropy that I've been using and just to add a constant k in front of that natural log of the multiplicity. The constant k is called Boltzmann's constant. It comes from pre-quantum mechanics times, before statistical mechanics was really understood at the level that it needed to be. Well, actually, should I tell you? Maybe that's not correct. That might not be right. I might be wrong about that. But in any event, Boltzmann's constant is 1.380649 times 10 to the minus 23rd joules per Kelvin. And so when if we put that in there, then we can get the entropy of a chunk of matter simply by multiplying that constant times the natural log of its multiplicity. And I should mention that entropy is what's called an extensive property. If I have more stuff, I have more entropy. Just like if I have more stuff, I have more energy. It's not the case that if I have more stuff, I have more temperature, right? Having more stuff doesn't make the temperature different. It just means that I have more energy and more entropy because there's more stuff there. It's an extensive property, whereas temperature is an intensive property. It's not a function of how much stuff I have. Okay, so this is where I want to bring Ben in to talk about the peculiar case of systems with limited numbers of places to put energy. And I'll just kind of introduce this and maybe let Ben say a few more words. The nice thing about it is that systems that have limited number of places to store energy, they will have a maximum amount of energy that they can store, but they have an entropy curve now as a result that starts and ends at zero. They have one way to store zero energy, and they have one way to store their maximum amount of energy. In between, there are multiple ways of storing energy, and so the entropy curve is going to look something like we show at the bottom there. Do you want to take it from here, Ben? I think this kind of sets you up. I'm not sure it's exactly what you were looking for. But...
Oh, no, that's cool. That's cool. No, I'm still here. So, yeah, well, the way I think of it, and do stop and correct and adjust, John, as I go. I'm going to try and keep it really simple. I'm going to imagine a system. It could be a laser, for example, as a real world system that could do it. And I'm going to imagine it's just got, say, I don't know, 7 particles, the same as the number of days of the week. And they can be, you might want to consider them to be like, I imagine them as marbles sitting in a solitaire board or something that can either be in a ground state, or they can just be lifted up into an upper state, and that's their only choice. They're either in a ground state or an excited state. So 7 particles, ground or excited. And then we start putting energy. So it starts off at absolute zero, and we start putting energy into this system. So at absolute zero, all 7 of them are just sat in their ground state. Now we put 1 quanta of energy in. The question is, how many different ways could that system absorb that? And the answer is 7. Any of the 7 could become excited. So that's a large increase in energy entropy, right? There's a big a lot of different ways, 7 different ways that you could absorb that quanta. So I think that's all good so far, right, John?
Yeah, sounds good.
Yep. So now
going in the right direction.
You're going in the right direction, up, yeah. So now we say, okay, what happens if I pump another quanta of energy into this thing? I turn the power of my laser up. Well, now you go from 7 different ways to 21. You have to think about that a little bit, but it's the mathematics is 7 choose 2, or you can just kind of think it through, and you'll realize that there's 21 different ways you can do it. So notice we've gone from 7 different ways to 21 different ways, and then you put another quanta in. So now how many different ways could that third one arrive? Well, there are 35 total ways that you can get 3 quantas of energy into the system. Then this is the bit that gets interesting, right? So the rate of increase of entropy as we add energy has at this moment, i.e. the temperature, been increasing. But when you try and add the 4th quanta of energy, you've now more than half of the particles in their excited state. And so there's, again, only 35 ways you can do that, the same as there were for 3. And then if you try and add 5, there's only 21 ways. And of course, there's only one way to add 7 quanta of energy to the system. So what happens is that the number of ways that the system can configure itself as you add energy initially goes up and up and up. It peaks at 35. And then beyond the halfway point, when more than half of them are excited, the system becomes more and more ordered. You start off by making it more and more disordered, and then you make it more and more ordered, because everything goes from all in the ground state to all in the excited state. And that inflection point at, in this case, I guess 3.5, not that you can add a half, is the point at which the temperature flips from positive to negative Kelvin. And that's pretty interesting, because the rate of increase of entropy with energy input flips to negative. You actually get a decrease in entropy. The system becomes more ordered as you push more particles into their excited state. So that's the noddy, harebrained way I think of it. So I just wanted to share that.
Was excellent.
Any use.
Excellent, and of course it's just what you described is exactly what that graph is showing, right? Increasing, kind of slowing down the rate at which it increases. It goes up to 21, and then only up to 35, and then start back down, right? Back down to 0, increasing the rate at which it goes down as the energy increases. And then just that thing. Remember that we decided that we were going to let temperature be 1 over the slope. So down there at energy, if you look at the graph on 13, down there near energy equals 0, the slope is pretty big. And so 1 over the slope is pretty small, technically, getting close to 0. It's positive, but close to 0. And as the slope decreases, the temperature increases because the temperature is 1 over the slope until at the top there it's infinite. The slope there is 0. 1 over 0 is infinity. Just to the left of the max, you've got positive infinity, and just to the right you've got negative infinity. Let's see, is that me? What's going on?
Yeah, that is weird. It sounds like it's coming from it sounds like background noise your end, is it not, John?
Oh, I know what it is. My wife is playing the stereo in the living room. I'm going to close my studio door. Hold on a sec. Yeah, it's funny. It gets picked up through my mic here, and I really can't tell where it's coming from. So anyway, that should be better. And then so then everybody here? I guess, am I still here?
Yep, you're all good.
Yeah, you're here.
Okay. Okay, good. So then on the other side, on the right side of that peak, now the slope is negative. It's very small, but it's negative. Very small negative. 1 over that is very large negative. And it continues getting hotter as the slope gets more and more negative until at the very end there, it's a very large negative slope, which means a very small, just the other side of 0, just the negative side of 0 temperature. So in fact, a temperature of negative 0.1 Kelvin is really hot, way hotter than infinitely hot. And whether you're talking negative infinity or positive infinity hot, a temperature of positive infinity is roughly equal to a temperature of negative infinity. And then as the temperature starts from negative infinity, getting larger and larger, moving towards 0, it's getting hotter and hotter. So as we go, so it's basically true that as the temperature gets larger, it gets hotter, except that at positive infinity, it all of a sudden jumps to negative infinity and then continues getting hotter from there as you get larger towards 0. Funny inverse kind of a thing. And this is really important in lasers, as Ben was alluding to before. In lasers, one of the really interesting quantum effects of photons interacting with atoms is that if you have an electron in a ground state, and a photon comes on with just the right amount of energy to promote that electron to a higher energy state, then the atom may absorb that electron and may absorb that photon and use the energy to promote that electron to a higher energy state. That's absorption. That's absorption of light. But there's for reasons that weren't understood before quantum mechanics, it turns out that the probability of that happening is exactly the same as the probability of a photon of that same energy coming by an atom that already has an electron in the excited state and causing that electron to jump back down to the ground state. So you've got a photon coming along with just the right amount of energy to promote an electron, but it finds an electron that has already been promoted. And what happens is that it causes that electron to jump back down and emit another photon of exactly the same energy as the one that stimulated the electron to jump down and emit its photon. The photon that's emitted is not only the exact same energy as the photon that caused the emission, but it's traveling in exactly the same direction, and it's in phase with the photon that caused it to that caused the electron to drop back down. This is called stimulated emission of radiation. And the probability of that happening is exactly the same as the probability of that initial photon being absorbed. So when a photon comes in, it might be absorbed by an atom, or it might stimulate that atom to emit another photon exactly like itself, thereby increasing its intensity by a factor of 2. The only reason that photons are generally absorbed rather than doing the stimulated emission thing is because most electrons are in the ground state. But if you can create what's called a population inversion, have more electrons in the upper state than you have in the lower state, then the fact that the probabilities are the same means that light coming in will be more likely to be amplified by the interaction than to be absorbed, simply because there's not as many atoms in a state such that they can absorb that incoming photon. But that's a very unusual situation, to have more electrons in a higher energy state than you have in the lower energy state, and it does reflect this negative temperature, the kind of thing where you're trying to put more energy into a system. You're butting up against the maximum amount of energy you can put into that system because you've promoted all those electrons. There's a lot more to it than that, but if
Is
you
this what
look at
happens
that
inside?
link,
Sorry,
so I'll
go
just
go
say,
ahead.
if you look at that link that I have there, the stimulated emission link, it just links to the Wikipedia article. It's kind of nice, and I think you will find that it makes contact with some of the things we've talked about. So go ahead, Shamash.
Is this what happens inside a laser? So
This is
that
what happens inside a laser.
you're
Yeah,
producing electrons that are in phase in the same direction, no
photons.
mistake whatsoever. So yeah, photons. What am I talking? Yes, of course. So
Right.
because of that phenomenon, so all the electrons are already in their maximally, let's say, excited state, and so all they can do is just emit those photons in that direction. Okay.
That's right. So the problem of a laser is how you maintain that inverted population, as it's called. How do once you have used all of those excited electrons to make this laser beam, now what? So the first lasers were pulsed lasers because the first thing you did was a process that promoted the electrons to these higher energy states, and then you let them kind of spontaneously create a laser pulse, and then you did it again. The process of making a continuous laser is a little more complicated, but it always involves this kind of negative temperature inverted population thing that's directly related to the entropy arguments that we've been talking about here
This
today.
is absolutely amazing, man.
So I'm done. I just wanted to mention one other thing, and then we can open it up to more discussion. Today, some of you may be aware, I'm probably more aware than just about anybody, that there's a thing called the final experiment that is been going on to take a bunch of people who believe the Earth is flat and a bunch of people who believe, I always hate saying that the Earth is round, just like all the pictures show it to be. And they're going to Antarctica to see if the sun actually does stay in the sky all for 24 hours in Antarctica in the winter. It's rather astonishing that there are people who think it's possible that it doesn't, since it's very well known that it does. But a guy named Will Duffy is personally putting out something like, I don't know, something on the order of $100,000 to take a bunch of flat earthers and globe earthers to Antarctica to see if the sun actually circles around their head. But there's a link there to the Final Experiment website, and there's an increasing collection of really humorous videos being put out by the flat earthers who are involved as well as the globe earthers who are involved. And I just commend it to your attention. It's happening today. I think they may be in their plane right now on their way down there. When they get there, they're going to go to a place called Union Station Glacier, and then they're going to look at the sun. And I've drawn here a picture of what the sun should look like on the standard standard so-called Gleason map model, where this time of year the sun is circling 3,000 miles above, 3 or 4,000 miles above the Tropic of Capricorn, which is a circle that they will be to the north of them. On the standard model, they are on an ice wall, part of the ice wall south of South America, and they'll be looking north, and they will expect to see their sun circling around over the Tropic of Capricorn, which is all to the north of them, getting smaller as it goes around to the back side of the Earth, and then so on. Whereas what they will see will be the sun circling around their head 33 degrees above the northern horizon at noon, and then circling all the way around to the back. I don't show in this picture to where it's the same size as it is at noon, but 13 degrees above the southern horizon, looking out in a direction where the flat earthers maintain there isn't anything. So anyway, it's really fun. I would, even if you try to avoid the flat Earth, this is a day to pay a little of attention. Will Duffy has hinted at there being some tension, a tense moment, and he's put out a video that is now released. I haven't had a chance to look at because I've been blathering on here, but there'll be a video at that site talking about this moment of tension and why he's glad it happened. So there's some clickbait for you. Okay, I just had to say that. But back to the topic. Any comments, questions, anything related to today's?
When we go back to slide 13 very quick, we've defined T as dE over ds, and we have a plot of S relative to E. What would a plot of E relative to S look like? And can we see the derivative probably there clearer? Because then we will see the tangent immediately.
Yeah, that's right. So of course that becomes a little more problematic in the case that I've drawn here, because E is not a single valued function of entropy. In other words, if I flip this curve, I'll find that for every possible value of entropy, there are two possible values of energy. So it becomes the whole question of when you start taking derivatives of things that are not functions in the language of math. Talking to you now, Shamash, things get a little more complicated. It's a little easier to see what happens in the more standard case, where entropy is a monotonically increasing function of energy that always curves downward. In that case, I think everything's pretty clear. But so ask your question again, because I think it's related to this particular case where it's a multi-valued function, right?
No, I just tried to draw it myself because I'm taking notes, and I just wondered to see whether what I see on my paper is the case or not.
Right. So if you do that, what you'll see, of course, in the standard case, what you'll see now is a function. If you graph it in the standard case, it'll just be a function that starts off with a small slope and gets bigger and bigger as the entropy increases, right? If I graph energy versus entropy, energy is an increasing function of entropy that increases at a faster rate as the entropy increases.
So it should look like what we started with, like some exponential going up, but then it
kind
turns,
of like
it loops back.
Except
the first half of
radical.
it looks like that, and then it loops back. Yeah, I see what happens.
Right. And so that should make sense, right? In other words, the slope is increasing with entropy, and that means the temperature is increasing with entropy.
Yeah, because on your slide you have positive temperature, and you say it's getting hotter all the time as you go to the right. I'm
Right.
supposing by hotter here you mean a higher heat, right? Like some more energy in the system, not more
Yeah,
temperature, because that what we have here is negative temperatures.
that's right. Yeah, when I said that's why I did use the word hotter. I didn't. I'd want to say higher temperature. Yet we usually think of higher temperatures meaning hotter, but it's kind of important since you can't really mathematically say that a negative temperature is higher than a positive temperature. It still is the case that a all negative temperatures are hotter than all positive temperatures, in the sense that it's always putting more energy into a system, more, yeah, just that. I'll just leave it at that.
That's absolutely mind-boggling. This is so cool.
Yeah, and it's fun because of the fact that it just does come back. You can do, if you go back to that formula that I gave for the multiplicity and see how it, the sense in which it becomes Maxwellian, and so you can really start talking about widths and all of the things that we associate, sorry, with Gaussian functions, I should have said. Yeah, it's just fun. A lot of fun with math. Statistical mechanics it should be really a blast for somebody like you, any mathematician.
Oh yeah, absolutely. I haven't studied this formally, but I'm looking forward for the chance when I get to get my, dirt under my fingernails because of this. This is so amazing.
Yeah, well, thank you. Let's see, any other things I haven't been watching? Oh, let's see what I did see somebody. Yeah, Kevin Filson remarked on quantum photonics, which I confess is not a room I often go into. It is definitely a great room for people who are interested in cutting edge physics presented by the people who are doing it. That's just absolutely the opposite of what I aim for here, because my aim is to stay away from cutting edge physics precisely so that we can do things a little more rigorously for people who are interested in science. And you should get people who are interested in science should do both. They should learn about cutting edge physics, but they should also then get their dose of rigor really from this place, because you can't talk about cutting edge physics rigorously to people to non scientists. I mean that's maybe a little bit of a too blanket a statement, but it's a problem that happens often. In my view, what happens a lot with cutting edge physics talks to lay people is that lay people come away kind of with a nice wow gee whiz feeling, but often because you have to kind of leave the mathematical rigor out. I think sometimes a lack of appreciation for just how rigorous it is. And those topics are typically extremely rigorous mathematically underneath the hood, a hood that you don't get to look under. So I guess I like to, in these talks, give a little peek under the hood of stuff that is a little more accessible, and therefore stuff that was typically done 100 years ago. So it's not cutting edge. But I totally agree with Kevin that people who are interested in science should definitely check out quantum photonics and other other places that do present cutting edge physics. Okay, so maybe we're done. Thanks for sticking around, you guys.
Can I have another one quickly, since no one else
Yeah,
has?
yeah, absolutely. Go ahead.
The graph we have on slide 13 kind of implies that you can get to a point where the energy is maximal and the entropy is null. So what happens after that point? Like let's say you have something and you keep giving it energy, and you've reached that state where, as in Ben's example, everything is excited now, and then what? You can't
Yeah,
give
well,
more energy. What happens then?
you can't put more energy into that system. I mean, it's possible depending on what you're talking about. You can imagine if you try to put more energy in that system, you now have a new system called a broken version of the previous system. But the point is, given the specifications of the system, that system has a maximum amount of energy you can put into it. So if you try to put more, you're just going to fail one way or the other. You're either not going to be able to put it in, or you're going to break the system.
Wow. Oh, wait a minute. This is not surprising. This is called, exciting something for chemical reaction. So heating sugar so that it burns. No, that makes
Yeah,
sense.
of course, what does happen in situations like that, we talk about, if you put more energy in, then real things melt or vaporize or become plasma or ionize, whatever. Um, so there's always
The previous system changes. That's the point. You
that's
will
right. It's
not
not
get
that
the same
system
thing as
anymore.
yeah.
That's right.
May I just say I'm really, really, really thankful for these series. It's just getting better and better. Like when I joined, let's say, what is it, 10 months ago that I made your acquaintance. I was like, these rooms are amazing. But right now, I'm like, what are we talking about? This is amazing. It's just getting better and better. And I know how much effort it takes for you to prepare these things. So I'm extremely thankful and really happy that we started recording these. I think this room in particular will be viewed by everybody and people will really
Everybody.
enjoy that.
5 billion
It should be.
views. Yeah.
It should be. This is the most simple, most straightforward, most wonderful and surprising episode on entropy I've seen, and I've seen most of them on YouTube, if not all. I watch these things all day, and this was absolutely to the point. So really, really big thank you for you.
Well, thank you, Shamash. I'm going to have to go get a pin for my head, I guess. But I do want to say, as long as we're kissing each other's ass, I do want to say I remember the first time you came into this room, you asking these sly questions as if you didn't have any idea what you were talking about, and it was immediately apparent to me that I was talking to a guy who was going to be hanging around. I was going to be hanging around with more. So uh, the feeling is
Oh, you
mutual,
got
and I,
that one right.
yeah,
I'm
yeah.
hanging out all the time here. I actually currently now this is my favorite place to hang out. And I'm not kissing ass. I'm saying absolutely. I have no play. If scientific discourse was on 24/7, I'd be there.
Well, it's not going to be on 24/7, so you won't be tested on that remark.
Yeah, this is a non-scientific claim because it can be falsifiable now. Anyway, yeah. So thank you, and hopefully we'll get these episodes right on YouTube. You can follow us at the Scientific Discourse. You will see all, well, not all yet, but hopefully at some point, all the previous episodes with their slides, and you can watch them again, refer to them again, tell your friends about them.
Well, anyway, and let me just once again also, for those of you who came in later, just really recommend the Philosophy Wednesdays, which happen at the same time on Wednesdays, that Shamash is doing, which really are a wonderful philosophy series because of their kind of emphasis on rigor, logic, the connections to science and math, etc. I find them equally stimulating, I think, to what Shamash
Oh,
is talking
that's
about
very
here.
flattering.
Yeah,
Equally
no, it's really
stimulating
good.
is very flattering. So next Wednesday we will talk about the similarities and or differences between math and physics. During the episode,
Cool.
I will claim that they are exactly the same exercise, and we'll try to convince all of you that it is. So this would be the first time I'm gonna kind of, instead of arguing all the different points of view that exist in the literature, I'm gonna try to force my own solution, let's say, or my own opinion on it at the end. So yeah, we'll do that on Wednesday, 17:30 GMT, same time as this room.
All right. Until then, everybody stay safe and walk between those raindrops.